Okay, so welcome back. We're going to be continuing with determinants today. So last time we had seen determinants of 2 by 2 matrices. Okay, so these were real numbers, okay, which you of course could have the formula A, B, C, D goes to AD minus BC. More importantly, what they represented was the signed area scaling. So measured the signed area scaling of any linear transformation associated to A. Okay, so you choose a basis. Once you've done that, A gives you a linear transformation, and then you can measure its area scaling, or signed area scaling, and that's what the determinant did. So today we're going to go into more general versions, okay, in which I mean higher dimensional versions, so determinants of n by n matrices. And I'm not even sure if I'm going to give the formal definition of these, but instead, at least what we're going to start with is saying what their basic properties are. They're going to be similar to the properties that we saw for 2 by 2 determinants, and then we're going to see what you can get from knowing those properties. Okay, and then I'll try to give an idea of how to give the formal definition. So the determinant of A is going to be an R. Okay, so actually you can think of this, it's kind of useful to think of determinant as going from n by n matrices to the real numbers. Okay, so it just takes a matrix and spits out its determinant. Again, we want to think of the determinant as measuring some sort of signed volume scaling when you think about this linear transformation from Rn to Rn. Okay, so what are kind of the properties that this should have? Okay, so the first is going to be that it's linear. Determinant is linear in each column. Okay, so in other words, if I take the determinant of a matrix, which looks like, I'll just say this is V1, and then I take the kth column and it looks like Vj plus, or I guess the jth column, V1 plus Vj prime. Okay, so this should be equal to the sum of the determinants, where you get V1 up through Vj, and so on, plus the determinant of V1 up through Vj prime. Okay? Similarly, oops, I forgot to put the word linear here. Okay, similarly, if I had determinant of V1 alpha Vj, this should be equal to alpha determinant of V1 up through Vj. Okay? So again, if you believe me that the determinant is some sort of signed volume of, well, it's going to be it's not a parallelogram anymore, it's kind of an n-dimensional version. So in 3 dimensions, you can at least draw the picture. It's called a parallel piped. Okay? You're measuring some sort of volume here. Then the columns of this matrix correspond to the vectors here. Okay? And these two properties come essentially from the same sort of reasoning that we used in the 2 by 2 case, right? So if I expand V1 to CV1, then I should get that the volume expands by C. Okay. Similarly, if I take 2 vectors and add them up, it turns out that the signed area of the parallel pipeds adds as well. Okay. So the next property is that column flips correspond multiplying by -1. Okay, so in particular, if I have V1 up through Vj, say up through Vk, up through Vn, and I look at the determinant here, this is equal to negative determinant of V1, Vk, so I flipped the j and kth rows. Oops. And then Vn. Okay? So flipping any two columns changes the sign of the determinant. And this is analogous to the fact that we're measuring signed area. So when we were looking at V and W, looking at this parallelogram, the signed area was negative that of V, calling this vector V and this vector W. Okay? So switching the order corresponded to a change of orientation so that we got an area of negative sign. The same thing happens. So let me just note here, we've also used a lot of geometric intuition for R2, but the determinant works for any matrix over any field. Okay, so you generally get something like a determinant which inputs an n by n matrix over F and then takes you to F. Okay, it's going to be the same formula as you would for the real n by n matrices, but you have, if you can imagine if I just have like a complex matrix, I have to think more about what it means for, I won't have the same parallel pipage that I can just take the volume of, right? There's something else is going on there. Okay, so that's another property. And finally, I'm just going to mention this, is that if I take the determinant of the identity matrix, this is the standard normalization, is that I get 1. Okay? And geometrically, this corresponds to the volume of an n cube, okay, which is always 1. Okay, you're just multiplying, well, you're taking things of length 1 and multiplying them together, so you get something of volume 1. Okay, so another property is that the determinant of A is going to be 0 if and only if A is not an invertible matrix. Okay, so this is something that we noticed was true for 2 by 2 matrices. The proof is the same here, so I'll just draw, something like the 3-dimensional picture. Again, if you have a notion of signed volume, then the determinant is 0 if and only if the image is lower dimensional. And in either case, this is if and only if. So this is the image, is this. And this is if and only if A is not invertible. So again, in all dimensions, the determinant is going to be kind of a test for non-invertibility. Let me just note that this, you can also see this from properties 1, 2, and 3. So the proof of this is kind of fun, so I guess I can do this. Okay, so first notice that any determinant, if I have 2 equal columns, so Vk and Vj, okay, so if these columns are equal, then the determinant has to be 0, right? Because in particular, I can flip the columns, and property 2, which I pull up here, property 2 tells me that column flips act by -1. Well, if I flip the columns, I'm getting the exact same matrix. So I better get that the determinant is equal to the negative determinant, which implies that it's 0. All right? So the same thing here applies if the columns, or one column one column is a multiple of another. Okay, again, you just use linearity, say that multiplying by some constant won't change the or changes the determinant by multiplication by that constant, but then they're equal, so the determinant has to be 0, so therefore the whole thing had determinant 0. Okay, so this also implies determinant is 0. Now, if I take A being non-invertible, okay, this is equivalent to saying there exists a column, okay, which is a linear combination of the other columns. Again, remember, these are only square matrices, and if a matrix is non-invertible, its image has smaller dimension. Okay, so you're going from, say, Rn to Rn, but the image is contained in some n minus 1 or less dimensional space. Well, the columns correspond to a basis for the image, so if that, if the image is smaller dimensional, it means that one of the basis vectors can be written as a linear combination of the other ones. Okay, so what we get is if we look at the determinant of V1, Vj up through Vn, okay, and let's just say Vj is equal to a linear combination of the others. Okay, let's just make it explicit. It's equal to the sum from k not equaling j, alpha k of the vector v sub k. Okay, now by linearity, we just expand it out, so you get the determinant of v1 up to this sum. Okay, so this is sum alpha k v sub k. Okay, up to v sub n. So you're just writing this column as a sum of the other ones, and by linearity, we know that we get that the determinant of, well, I'll just say it's the sum of determinants of these matrices, alpha k v sub k, okay, for k not equaling j. Notice by construction, all of these matrices are going to have determinant as 0. Okay, so if this column is non-zero, then by construction it's equal to a multiple of another column, right? So if the alpha k v sub k is non-zero, then it's equal to exactly alpha k times the column v sub k. Okay. On the other hand, if it is 0, then the determinant is 0 by linearity again. Right? If I have a 0 column, then I can multiply by that column by 0. I keep the same matrix, but now by linearity my determinant is 0. Okay? So either way, I'm either matching up one of my columns, or I have a 0 column. So I'm taking a sum of determinants, which are all 0, so therefore I get 0. Okay, so therefore the total sum, which is precisely the determinant I'm interested in, is 0. Okay, so actually the same argument gives kind of a useful proposition. Okay, which says that the determinant does not change. Essentially, if we do column operations, does not change if we do column operations. So what that means is that we can add a linear, so you have to be a little careful. So for example, you can't flip the columns like you do with row operations, because now you're changing the sign. But what we can do is add a linear combination of columns to a different column so i.e. add a linear combination of columns to a different column. Okay, so we can do kind of similar operations that we do with row operations so to try to put our matrix into a simpler form, and if we're careful, we can do this without changing the determinant. Okay, so this again is going to be useful for computing these things. Okay, so those are properties. Let me give you now two computations, again, that you can get essentially from these properties. So the first one is very simple. So if we have a diagonal matrix, okay, so this will look like lambda 1, lambda 2 up to lambda n. 0 is here. Then the determinant is equal to the product of the diagonal entries. Okay? So the proof of this is just linearity, a very special linearity. Again, I'll just say again, okay? So you start with the identity, which we know has determinant 1, and then you multiply the ith column by lambda I. Okay? So that gives the computation for diagonal matrices. It's a little more involved, but essentially a similar argument will give you that upper triangular matrices have the same formula. Okay, have the same formula. That is, if I put lambda 1 up through lambda n. Now, I'm just saying this is now allowed to be anything. Okay? And this has to be 0. Then we get the determinant again is the product of the lambda i's. Okay? So, how do you see this? Well, these can all be converted. So these can be converted by column replacement. Okay, by column operations. Into diagonal matrix with the same diagonal entries. Okay, so that certainly, since those preserve the determinant, that does it. Okay, and this is just like converting, or similar to converting a matrix in reduced echelon form. Okay, so there's all zeros here. You use lambda 1 and column operations to turn all of these into 0. Similarly for lambda 2 and so on. Okay, so those are the column operations. You just multiply by the appropriate coefficients to turn all these into 0, and you haven't changed the diagonal. Okay, so I should say that this works if the lambda I are not equal to 0, but it's also easy to check that if lambda I is 0, then the matrix is not invertible. Okay, and hence you get determinant 0. Okay, So actually the same thing occurs up here, right? If I had a determinant, or if I had one of the lambda i's being 0, then I would have a row of all zeros, if you wish, so that we know that this can't be an invertible matrix, or a column of all zeros. I mean, you're sending something to the 0 vector. Similarly here, you kind of go to the first, if there's a 0, you go to the first vector, and then use column operations to make the entire column 0, right? So there are zeros below by assumption, and then you can use column operations to kill the zeros above. All right, so in any case, you can get a column of all zeros. That gives you something automatically in your kernel. Okay, so now let me tell you two important theorems, one of which we've seen before. Okay, so the first is that the determinant of A transpose is equal to the determinant of A, okay? And the second theorem we have seen, it's the determinant of AB is equal to determinant of A times determinant of B. Okay, so the first one we saw was essentially came from this intuition we have about, or in the two-dimensional case, the fact that we showed the determinant is measuring the signed area scaling, okay, and then composition makes that scaling multiplicative. We didn't show the A transpose one, and actually it's something that does follow immediately from the formula. Okay, but if you just look at a geometric picture, so maybe I'll draw a vector AC and BD, okay, which I'll put somewhere up here. Okay, so we get this parallelogram. So I'm thinking of B as less than C, okay, and D is larger. So then if I'm looking at the transpose, I will take the matrix, or I take the coordinates AB. Okay, so that goes somewhere. And then CD goes a little here. Okay, notice the vectors here are the same. So you can imagine that these will have the same area. Certainly if you know the formula for the area of a parallelogram, they will, but it's not completely obvious that they do. Okay, and you can draw different pictures where the shape of the vectors for A versus the shape of the vectors for A transpose look different, but they end up having the same area. Okay, so let's prove these. The basic idea is going to be going back to something very similar to reduced row echelon form, or the work that we did to make that happen. It's going to be slightly different because we're looking, when you're doing determinants, you're looking at these parallelograms spanned by vectors, so it's natural to look at the columns. Everything else is going to be the same, okay? So let me start with this lemma, which says that if you take a matrix A, again, I'm always assuming it's a square matrix, okay, and an elementary matrix, okay, then the determinant of AE is the determinant of A times the determinant of E. Okay, so this is just an easier case of this theorem here. Okay, and notice, I should say this right multiplication. So we saw left multiplication by elementary matrices when we were doing row operations. Right multiplication by E corresponds to a column operation.
Okay, and now the proof is, well, you just calculate the determinant for each column operation or each type. Okay, so to calculate the determinant of E for each type, there's going to be 3 types corresponding to each row operation, and it will turn out to influence the determinant in the same way as the determinant of E. Okay, so the first one is adding multiple of one column to another, all right, so this corresponds to multiplying by a matrix with ones along the diagonal and one non-zero term in a single slot. Okay, everything else is zero. So this has the effect of not changing the determinant. Okay, so the determinant of AE is going to be the same as the determinant of A, and this will have determinant 1. Okay, so in this case, you could get this from computing with the formal definition. On the other hand, you can just realize this is, well, it's a triangular matrix, so depending on where alpha is, this is either upper or lower triangular matrix. I didn't say anything about lower triangular. The same exact proof works, so you're going to get the determinant is the product of the diagonal entries, so you just get that it's 1. Okay, so the second one is multiplying a row, or sorry, multiplying a column. So this corresponds to the elementary matrix where you just have ones along the diagonal, some non-zero term, and zeros everywhere else. Again, this has the effect of multiplying the determinant by alpha, okay, by one of our basic properties. On the other hand, the determinant of this is alpha. Okay, so multiplying the matrix or just multiplying the determinants has the exact same effect. And similarly, there's switching columns, okay, which you obtain multiplying with the elementary matrix with ones along the diagonal, and then a 1 and a 1 here, so I'll just put it like this, and then ones. So what I've done is exactly switch the row and switch the two columns of the identity matrix. Okay, and since the identity matrix has determinant 1, if I've switched two columns in the identity, then I get that this determinant has to be -1. Okay, by our basic property. Okay, so that proves the lemma essentially by computation and checking all the cases. Of course, now the power of this is that we can multiply on the right by many elementary matrices, and we know exactly what goes on with the determinant. Okay, so let me just say this as a corollary. If I look at the determinant of A, E1 up through En, okay, so you should think I'm taking my matrix and I'm doing any number of column operations. Well, I know what to do, or I know how the determinant behaves under all of them now. It's going to be the determinant of A, determinant of E1, up through determinant of En. Okay, so now what we can do is, essentially this reduces the two theorems that I wanted to show to checking the case of elementary matrices. Okay, so what we have now is that for any invertible matrix, matrix A is the product of elementary matrices. Okay, so we've seen this when we were putting matrices into reduced row echelon form, right? We saw the invertible matrices would have reduced form the identity, and then the operations that you did to that corresponded to elementary matrices. So we would get like A, now we're multiplying on the left because we were doing row operations up through En is equal to the identity. So A is equal to E1 inverse, E2 inverse, up through En inverse. Okay? Now, if you want to show, so to show the determinant of A is equal to the determinant of its transpose, well, we can write A as a product of elementary matrices. Okay, so we get E1 I'm just going to write it now as E1 up through En. Of course, these are really inverted, but now just call the inverses the matrices. So the determinant of E1 through En, the claim is that this is equal to determinant of E1 up through En transpose. Okay, but this is the determinant of En transpose up through E1 transpose. Now by this rule, all we know, so over here we have determinant, maybe I'll just write it in shorthand, we have the product from I equals 1 to n of the determinant of the EIs, and here we have product from 1 to n, determinant of the EI transpose. Okay, but for every elementary matrix, these are equal, which again, you just go through the three cases, and you can check that this is satisfied. Okay. Okay, and at least in the 2x2 case, this all came from, or you could see it geometrically with this signed area, right? The elementary matrices were either shearing, or they were multiplying one of the vectors by a column or by a scalar, or they were flipping the two vectors and therefore flipping the signed area. Again, you can see this kind of geometrically if you're working with parallel pipeds in R3. But I think it's kind of nice that you get basically a totally non-obvious theorem, okay, just from knowing a couple of the properties that a determinant function would have to satisfy, okay? And in an exactly similar way, you also get that the determinant of AB is equal to the determinant of A times the determinant of B. Well, just write down the elementary matrices again. Okay, so AB, or A and B are written by elementary matrices. You write them all out, write them all out, write them all out here. You have the same exact sequence of matrices, and then you just use this corollary here. Okay? Okay, so now let me give you an idea of the formal definition of determinant. Okay, and then there's a couple ways to compute the determinant that I'm not going to talk about too much. Okay, so let me give you, what's the idea of a definition? Well, what we want, let's just say what we want. We want the determinant to be a function which goes from Mn to R, and we want it to be linear in the columns. Okay, so linear in each column. Okay, so if I take a linear combination of any column, then and I take the determinant, it's the determinant of the linear sums. And you wanted the identity to be 1, okay, just somewhere to start, and then we wanted switching columns corresponded to multiplying by -1. Okay? Once we had these three properties, we are able to deduce everything we wanted about column operations, so elementary matrices, and then we extended everything to arbitrary matrices. Okay? So what does this have to do now? So, well, if I take any matrix V1 up through Vn, so I'm assuming I just have n vectors in R to the n, well, I can write these all in the standard basis, okay? So we're going to essentially start from the fact that we know the determinant of E1, E2 up through En, okay, where these are the standard basis vectors, and I can decompose every single thing in terms of those standard basis vectors. So I get something which looks like the determinant of, well, it looks something like, the sum of the alpha I E sub I, sum of the beta I E sub I,
and so on. Okay, this is where the notation is terrible, but I'm trying to do a very simple thing. Just each column in terms of standard basis vectors, and then since it's linear in the columns, you get this huge summand. So I'll just make it a big summand. I'm not going to try to keep track of what I'm summing over. And what I end up with is terms which look like the determinant of matrices with exactly one non-zero column, or one non-zero entry in each column. So I don't know, it'll look something like 1, 0, 0, 0, 2, 0, 0, 3, 0. Okay? Or, 0, 1, 0, 1, 0, 0, 0, 0, 5. Okay, so these are the end. Once you've split up these, right, so these all look like alpha I e sub I, beta I e sub I, all these sums. You just write them all out. Just imagine doing a huge distribution, and you'll get a bunch of matrices that look like this. Okay? And now we're taking the determinants here. Well, luckily, this is now a huge sum. Okay, but luckily, most of these will have determinant 0. Okay? Okay, so this occurs anytime I have two columns that are multiples of each other. Okay, so i.e., that are multiples. So i.e., if an alpha vector, so I'll just say if I see ei is used twice, at least twice. Okay? So you imagine you're writing these all down in terms of the standard basis vectors, distribute them all out. So maybe I'll just do 2 by 2 case. Okay, so this is A, and I did this in the last lecture. So I have AE1 plus BE2, CE1 plus DE2. Okay, these are my two columns. And I'm getting AE1 CE1 plus AE1 DE2 as columns, plus BE2 CE1 plus BE2 DE2. Okay? So the determinant of an arbitrary 2 by 2 matrix would have to be the determinant of these four sums, but these are 0. Right? Because if it satisfies the property of linearity, it has to satisfy the property that if I have one column that's a multiple, then I get 0. Okay, so these are the only two to worry about. And similarly, you can imagine when you write out these now in terms of n, now you're distributing n variables or n vectors, you're going to get tons of matrices that look like this, where you've used the same basis vector twice, and, well, unfortunately still a ton of matrices which look like this, where you've only used each basis vector once, but in a different order. Okay? But now these are the only ones that you have to check about. Okay, so how do you do this now? Well, again, in the 2 by 2 case, you now have two matrices to worry about. You have to work out what the determinant is of AE 0, 0 and 0, 0 BC. Okay? So these were the two matrices, of this form, right, that come into the calculation. Okay? So what do we do here? Well, in this case, we know this one. By linearity, this has to be AD. And here, we switch the switch the columns. So this determinant has to be, again, by linearity, plus switching columns, negative BC. Okay? So you can do the exact same thing for these matrices that we're worrying about. Okay? that are now n by n. So if I have a matrix of this form, where there's exactly now one non-zero term in every row or column, row and column, exactly one, right? If I didn't have this, then the determinant would be 0. So we'll see something like beta, and then a thing of 0 is 0 lambda, okay? So there's some number of column switches that will produces a diagonal matrix. Okay, so with some number of column switches, you can get to beta, lambda, gamma, alpha, and so on. Okay, should have used one Greek letter. Okay, so there's some number of column switches, which it'll turn out that you can work that out exactly. But once you're at this point, we know that the determinant here, if it's linear, is just going to be the product of the diagonal terms. Okay, so now let me talk just a little bit more about this. Okay, and then once we've kind of handled this number of column switches, we'll essentially be done. Okay, so you should think we have n columns in the wrong order. Okay? In other words, it's not a diagonal matrix. And what we want to do is do a permutation. So permute the n columns so that we have n columns in the correct order. Okay, so that it is diagonal. So what happens here, I mean, we can identify this as just we have some, well, I'm going to identify the columns with 1 through n. Then we have a bijection to alpha 1, alpha 2, up through alpha n. And we want to write this in terms of column switches. Well, it turns out, this isn't obvious at all, but it turns out that alpha is a composition of switches, okay? So in other words, they just correspond to the column switches. If you have any bijection from the set 1 to n to itself, it's a composition of, just switching the ith and jth terms, okay? And then the important thing is that the number of compositions of switches, or the number of switches, well, again, it doesn't really, it might, depend on exactly what you do, but at least the number of them mod 2 is well defined. Okay, so there might be a lot of different ways to write alpha as a product of switches, but it's always going to be an even number of switches, or it's always going to be an odd number of switches. Okay, so let me just put in an example. So if I have, say, 1, 2, 3, and I'm going to send this to 2, this to 3, and this to 1, so this is like a cyclic permutation. This is a composition of, well, first sending 1 to 2, 2 to 1, and 3 to 3, and then sending 1 to 3, 2 to 2, and 3 to 1. Okay, so if I do this flip first, I send 1 to 2, then this fixes it. So I go 1 goes to 2. Similarly, 2 goes to 1, then goes to 3. 3 goes to 3, then goes to 1. Okay? Of course, I could have written this as flips in many different ways, but it'll always be even. Okay? And if you want to look it up, this is called sign of a permutation. can also Google the symmetric group, which is just the group of permutations on n letters, or n element sets. Okay, and then you'll quickly find these concepts defined and more of their properties. Okay, so now once we get to from here to here, what we've done is, we're doing this number of column switches. This number of column switches is well-defined mod 2. And what the properties, the determinant means is that we're going to be multiplying by -1 or 1, but it doesn't matter, how we got to the diagonal place. Okay, so this process is now well-defined. And at this point, we have defined the determinant. Okay, so actually what we did is we said, well, there's, it has to have these 3 properties, linearity, switching columns, and the identity has to have determinant 1, okay? But actually this is the way that we can say that the determinant is defined. So if you want to figure out like what the determinant of, A, B, C, D, E, F, G, H, I is, well, you would write A, D, G as, A times 1, 0, 0 plus D times 0, 1, 0 plus G times 0, 0, 1, etc. Expand all of it out, bring everything to these forms, these diagonal matrices, and then take the product. Once you add them all up, that's just what the determinant is. Okay, so it shows that it's the unique function satisfying this property, but it also can be the definition. So of course we lose, in the nice geometric intuition that we had in the 2x2 case. Now it so happens that in the 3x3 case, as I mentioned, you can look at, signed volume of parallel pipeds. Okay, and there's also easier formulas for the determinant of a 3x3 matrix, okay, which you can easily find. And in general, you are, in the n by n case, you are measuring the signed n volume of the scaling of these parallel pipeds, but, we have to kind of define what that means, and usually the way, or a number of the ways you see it defined is people just define it in terms of the determinant of the n by n matrix. Okay, so it's slightly circular. Okay, so I think what I'm going to end, instead of giving kind of an application of the determinant, I thought I'd just give kind of a beautiful formula, sketch how it's proved. Okay, it's the formula that might be a little hard at first to appreciate, but it turns out to be useful in a number of examples throughout mathematics. Okay, so first I have to tell you what exponentiation is in this context. Okay, so A is going to be a matrix. E to the A. So I'm going to want the idea of an exponentiated matrix. So it's going to be 1 plus A plus A squared over 2 plus A cubed over 3 factorial plus ... Okay, so I know this is kind of well defined at this point. I know how to multiply matrices. I can add them, divide by scalars. You have to worry a little bit about what it means, what this ... means. I'm essentially taking the limit. So the ijth term here is just the ijth term of the partial sums. And since exponentiating is really nice and you're dividing by factorials, it turns out that everything is going to converge. Okay, so every matrix entry here converges, for any matrix A, converges to this matrix entry here. Okay? So why do you want to do this? Well, there's a nice formula, which is that, so I'll say this as a theorem, the determinant of e to the a is equal to e to the trace of a. Okay, so there's this kind of unification between determinant and the exponentiated trace. So let me just give you as a corollary. This tells you since the trace, since e to something is always non-zero, e to the a is an invertible matrix. For all a. Okay, so this is kind of a nice thing to do at some points. If you have a matrix that's not invertible, you can exponentiate and turn it into an invertible matrix, right? So this is similar to taking a function which might have 0 values and then looking at e to the f of x, and all of a sudden you have a function that never takes on the value 0. Okay, which is sometimes useful. Okay, so let me give you the idea of the proof of this. I think it's also nice that kind of these two similarity invariants that we've come up with, turn out to be related in some way. So first note, this is true for diagonal matrices. Okay, so if I take, I'll just write the 2 by 2 case, if I take lambda 1, lambda 2, and I look at e to this, well, it's easy to see that this is just e to the lambda 1, e to the lambda 2, okay? In this case, the matrix multiplication is quite simple. And therefore, if I take the determinant of this, e to the lambda 1, e to the lambda 2, 0, 0, I'm getting product of the diagonals. On the other hand, if I take the trace of a, so if I get e to the trace, then I'm getting e to the lambda 1 plus lambda 2. Okay? And therefore, by exponentiation rules, I get that these are equal. So now you can also see that this is also true for upper triangular. The proof is exactly the same. Okay, or actually you can just say or lower triangular. Okay, so what happens if you take an upper triangular matrix, maybe I'll do the 3 by 3 case. If you start raising this matrix to powers, the things that you'll see in the diagonal are just the powers of the diagonal terms. Everything here becomes more complicated, but when you're taking the trace, you only care about the diagonal terms, and when you're taking the determinant of a triangular matrix, you only care about the diagonal terms. Okay, so if you believe that, and you believe the statement about the multiplication, then you get that the same argument essentially will give you that it's true here. And finally, it turns out that any matrix A is similar to a triangular matrix. Okay, and here I am slightly lying just a little bit. So it's not true over the real numbers, which that's a good example to think about, something that wouldn't be similar to a triangular matrix. It happens to be true over the complex numbers. So we can just kind of work with the complex numbers and notice that the determinant and the trace, though I've only been kind of thinking about real numbers, extend in both cases. Okay? So what you get is that A is equal to, say, PT P inverse. I should note here, if A is not invertible, then T will have a 0 on the diagonal. That's certainly fine. And in that case, you should check what's happening with both the trace and the determinant. Okay, so now we're looking at e to the a. Well, again, this is 1 plus a squared over 2 plus dot dot dot. This is equal to 1 plus PTP inverse plus PTP inverse squared over 2 dot dot dot. Now notice that PTP inverse squared is just PT squared P inverse. So this is 1 plus PTP inverse plus P T squared P inverse over 2 plus dot dot dot. In other words, this is P e to the t P inverse, so the determinant is just the determinant of e to the t. And the exact same thing happens for the trace. I'm getting the trace, or e to the trace of p t P inverse is e to the trace of t. Okay, so once I've started with my matrix A, if I've gotten it being similar to a matrix which is upper triangular, then I can immediately, since both of these are similarity invariants, just deal with the upper triangular case, which is what we showed before. Okay? So therefore, it's true for all A. Okay, and I think this is already a pretty long video, so a good place to stop. Okay, so thanks.